Hello friends, today we're going to discuss the topic of specific electric loading and specific magnetic loading of three-phase induction motor while designing. The specific electric loading or ampere conductors can be obtained from the output equation of three-phase induction motor, which is given as d square L is equal to Q C0 Ns, where d is the stator bore diameter in meter, L is the length of the stator core in meter, Q is the input kVA of the induction motor, C0 is known as the output coefficient, and Ns is the synchronous speed in revolution per second. And this synchronous speed is defined by the number of poles and the frequency of the supply. So the output coefficient of a three-phase induction motor is given by pi square AC BAV into 10 to minus 3, where AC is known as the specific electric loading or ampere conductors of the induction motor. BAV is known as the specific magnetic loading, or it is also the average flux density in the air gap. So the ampere conductors of a three-phase induction motor, which is also known as the specific electric loading, is given by IZZ upon pi d, where IZ is the stator current per phase in ampere, Z is the number of armature conductors, which is also given by 2m TPH, where TPH is the number of turns per phase, M is the number of slots per pole per phase, and D is nothing but the stator bore diameter in meter. So generally the range of this specific electric loading is from 5,000 to 45,000. Now the designer has an option to select any value from this range of 5,000 to 45,000. So what are the parameters which the designer has to take into consideration while choosing a particular value of AC? Let us discuss. The choice of specific electric loading will basically depend upon the four parameters. Firstly, the copper loss, temperature of the machine, overload capacity which the motor can take up, and of course the supply voltage for which the motor is to be designed. First, the copper loss. The copper loss of the induction motor we know is given by I square R. So definitely the value of ampere conductor, if it is taken higher, then the value of the current, input current to the motor will be high. Similarly, for higher value of ampere conductors, the number of conductors would be more, and if the conductor of stator are more, then its resistance will be higher. So both current as well as the resistance will increase for the motor, and it will lead to higher copper loss. So in order to reduce the copper loss, we must select the value of specific electric loading which is lower. The maximum temperature rise of the motor is also governed by the amount of loss which is taking place in the motor. If you select the higher value of ampere conductors or specific electric loading, larger current will be flowing in the motor, which will lead to larger copper loss. If we do not have sufficient cooling surface or effective medium for the heat dissipation, then the temperature will rise. If we are having a totally enclosed type of motor, then definitely the value of ampere conductors selected should be less. So depending upon the working condition or the medium of cooling, we can select the value of ampere conductor. So temperature rise should not go beyond its permissible limit. The overload capacity. Higher value of ampere conductors will mean that more number of stator conductors are going to be employed in the motor. This will lead to higher leakage reactances in the motor, and this higher leakage reactance will definitely lead to a circle diagram of the motor which is having a smaller diameter, hence the circle diagram will be smaller, which means that the lower overload capacity will be obtained. It can also be looked from the other point of view that for higher temperature rise, we will require lower ampere conductors as discussed. So if motor rises to a greater temperature, then it cannot take up the additional overload capacity, even if it cannot take up the full load capacity. So in order to have more overload capacity, we must select the value of ampere conductors which is comparatively lower. And finally, the voltage. We know that ampere conductors is nothing but the number of conductors which will be accommodated in the slot. The slot of stator of three-phase induction motor consists of the conductor along with insulation, because there will be requirement of insulation between the turns as well as between the slot wall and the conductor. So if we have a motor with higher voltage, then the amount of insulation requirement will be more as compared to the requirement of the conductor space. So we cannot select a higher value of specific electric loading from the voltage point of view. So higher voltage motors will have comparatively lesser ampere conductor or specific electric loading. Similarly, let us discuss the specific magnetic loading. The specific magnetic loading is nothing but the average flux density in the air gap. The output coefficient of the induction motor is given by pi square AC BAV into 10 raised to minus 3, where BAV is known as the specific magnetic loading. It is having a unit of Weber per meter square because it is nothing but average flux density of the air gap. It is given by the formula P phi upon pi dl, where P is the number of stator poles, phi is the flux in Weber, d is the stator bore diameter in meter, and length of the stator core L in meter. So the range for this specific magnetic loading is from 0.3 to 0.65. 0.65 is generally selected for say cranes or hoist or rolling mills type of applications. Otherwise the range is basically from 0.3 to 0.6. Again, here the designer has an option to select any value of BAV. So what are the parameters which the designer must take into consideration while selecting the specific magnetic loading value? So we are having three factors which we must take into consideration while we have the choice of specific magnetic loading. It's power factor, iron loss, and overload capacity. The lower value of specific magnetic loading will mean that there is smaller or lesser flux per pole. So to set up this flux in the air gap, we will require lesser value or smaller value of the magnetizing current. So magnetizing current will be less. If the magnetizing current will be less, that means the no load current of the motor will also be less, and it will be more nearer to the voltage phasor. So the power factor angle will be small, and hence the power factor will be high. So for lesser value of specific magnetic loading, the power factor will be high. But again, if we select higher value of BAV, there will be also one more problem that is nothing but saturation of the core. So while selecting the value of flux density, we must also take into consideration that that material should be able to take up that flux without saturation. So its value BAV should be always be less than the maximum flux density BM of the core material. Next is the iron loss. We know that iron loss has got two components, namely hysteresis loss and eddy current loss. Both these losses are dependent on the flux density. Higher value of the flux density will increase the hysteresis loss, as it is having a power of 1.6, and the eddy current loss, which is having a power of 2. So both hysteresis as well as eddy current loss will increase with higher value of BAV, which will lead to lower efficiency of the motor. Again, specific magnetic loading can also affect on the overload capacity. We know that higher value of average flux density will lead to higher value of flux, and this will cause lesser leakage reactance with bigger circle diagram. So definitely the overload capacity will be higher for higher value of specific magnetic loading. Thank you friends. If you like this video, kindly do comment on it and please subscribe. Thank you.